So for today, I'm going to start off with going over or starting to go over the physical science section of the science test. So I'm going to share my screen here. So give me a second to pull this up. And let me know if you can't see this. Hopefully you can. To kind of start with, we're going to talk about matter and states of matter. So when we're talking about matter, we're talking about essentially what stuff is made of, right? So today I'm going to try to talk in general terms, and tomorrow we'll probably talk in more specific terms and talk about atoms and how atoms are constructed. But for today, I just want to talk about matter in general and kind of look at it from just a basic point of view. So let me see. So if I was to go, hold on, I'm scrolling around, losing my place. All right, just making sure I'm in the right spot. Boom, that's where I wanted to be. Okay, so when we're talking about matter, and we're talking about changes in the state of matter, we're talking about solid, liquid, gas, essentially. And there's a little more to it than that, but for the sake of simplicity and what you need to know on the GED test, you really just need to know solid, liquid, gas. There's actually a state below solid and a state above gas, but that's not the type of thing that you're going to see pop up on the GED. So the best example I can give to kind of go through this easily and quickly would just be talking about water, or let's use H2O as kind of an example. So when we think about water, water in its solid state is ice, right? So frozen water is solid, it's suspended, the particles aren't moving around. So if you look at the picture, and this is one area where water is actually a bad example, because solid water is actually less dense than liquid water, but that's not normally the case. So typically, when you have a material in its solid state, particles are, and when I'm talking about particles, just these little bits, and I don't know if you can see my little cursor or not, but the little red dots, right? They're all closely packed together, so more dense again, not moving around, and not changing shape, right? So when you think of something that's a solid, anything, right? Like this desk or the computer or anything, right? You know what a solid is, right? My coffee, right? So this is solid. It's rigid. The material or the particles that make this up are tightly packed together, and it's not going to change shape or change volume, right? So it has a fixed shape and a fixed volume, right? This isn't going to morph into a different shape. When I also think of solid and how the particles are packed together, I think of, can you put your hand through something, right? That's a solid. Right? If we're talking about the wall, right? You can't put your hand through the wall. You can break the wall, but you can't actually slip your hand through the particles that make up the wall, right? So that's kind of the best example of how I can describe anything that's in a solid state. It's easy to identify when things are solid, but try to define it, it can be a little more confusing. And so just thinking of it in terms of rigid, it has a fixed shape and a fixed volume. The fixed volume part of it is it's not going to get bigger or smaller, right? It's going to stay the same size and the same shape. So as we transition from solid to liquid, the particles tend to spread apart and they start to move around. So think about a liquid, right? Think about liquid water, okay? It's not rigid in that there isn't really a shape to it, right? There's no fixed shape. Liquid takes the form of whatever's constrained, right? So if I fill this with coffee, liquid coffee inside of it takes the shape of this thermos, right? But if I pour that coffee out into a cup, it's now changed shape, and now it's the shape of the cup, right? And if I dump it on the floor, then it just spreads out and it takes the shape of the floor and just lays flat until it evaporates, right? So liquid has no fixed shape whatsoever. But at the same time, it does have a fixed volume. So remember, when we're talking about volume, think about math when we've talked about volume, because I know you love math, Aaliyah, right? But when we talk about volume, we're talking about the amount that can fit inside. So if I fill this to the very top with coffee, right, and I pour it into a tiny cup, it's not all going to fit, right? That's obvious. Likewise, I can't take a tiny cup of coffee and pour it into a giant jug and all of a sudden create more coffee, right? So liquids have a fixed volume, but no fixed shape, okay? And when we talk about the little particles, so you can see the little dots floating around in the liquid, just imagine that's the molecules of H2O, right, that make up a glass of water. Those molecules are actually moving, and we're gonna probably get to talking about why that is today. I'll try to kind of go through this quickly, and then we'll, like normal, end with a couple practice questions. So as we go from solid to liquid, and now liquid to gas, notice when you see the green dots that make up the molecules of gas, right, they're even further spread apart, right? So the molecules are farther apart and they have more energy. They're moving around even faster, okay? They're definitely not rigid. So when we think of a gas, think of air, think of water vapor, think of any gas you can think of. But when something is in a gaseous state, right, it's not rigid, it has no fixed shape, right? So the air we're breathing right now is the shape of the room, essentially, right, or whatever, right? Gases will, just like liquid, gases will fill whatever space they're confined to, right? The difference between a liquid and a gas in terms of how they act, whereas a liquid has a fixed volume, a gas does not, right? So a gas, and this goes back to, because the molecules are so spread apart in a gas, you can actually condense gas down and squish it and make it small. Whereas you can't take a bottle of water and squish that water down and make it smaller, right? But with gas, think about like an oxygen tank. So an oxygen tank, when you're breathing, if you're scuba diving or if you're sick and you're on oxygen, right? The oxygen in that tank is condensed oxygen, right? It's pressurized down to fit a lot of oxygen gas into a small canister. And the way you can do that is because, or the reason you can do that, not the way, the reason you can do it is because it's all so spread apart that it's easily condensed, right? Through pressure. Pressure would be how you would condense it. Likewise, if I take that, so if I have an oxygen tank, imagine this is filled with oxygen gas, condensed oxygen gas. If I was to open it up, first of all, it'd probably like explode. Secondly, all that condensed oxygen would spread out and it would fill up this room, right? And all of a sudden now I have a greater volume of oxygen gas. Gases are different in that regard, in that they not only have no fixed shape, but they have no fixed volume, right? So these two different pictures here, you can see they're basically telling you the same thing, right? So I kind of went through and described the one in the upper left, but the bottom right here is essentially saying the same thing. Solids hold their shape and have a fixed volume. Liquids fill the shape of the container, but have a fixed volume. And gas fills the shape of the container and fills the volume of the container. So that's kind of just a different way of explaining the same thing. All right, so what drives the change from solid to liquid to gas, right? And this is kind of weird because I, again, can't hear or see anyone, so I'm kind of like talking to myself here. But think about that, right? And if we take water, if we go from ice to water vapor, right? What factor, haven't mentioned goes into driving that change, right? And the key is, right, which is a form of energy, right? So the reason that the gas molecules are moving around faster is because they are more energized than molecules in a solid, right? So when we go from one state to the other, we're essentially adding heat energy, right? So when we take frozen ice, right? So we've got ice. To get that ice to turn into liquid water, we have to add heat, right? That seems logical. So any time we have a solid that turns into a liquid, and so now I'm kind of going off of this slide here, right? We call that melting, right? To turn a solid into a liquid is to melt it. So we usually think of that with water. That applies to any time we're taking a solid and we're turning it into a liquid, right? We use that term, okay? Going from liquid to gas, right? It would be vaporization, boiling, right? When we boil liquid water, those bubbles, right, water is evaporating and turning into water vapor, right? Or it's just like little particles of H2O in the air. That's why it's humid feeling, or you see the steam, or whatever you want to call it, right? So again, we go from solid to liquid by adding heat. We do the same thing, right? We go from liquid to gas, we keep adding more and more heat, and eventually it changes, right? So, and if we were to keep energizing gases, right, you can get gases to turn into the fourth state of matter, which is called plasma, right, which is like a super heat energized state of matter that's even beyond gas, right? But we don't need to go down that road today. Now going back down the other way, so from gas down to liquid, down to solid, right? That change is also driven by heat. It's just the removal of heat, right? So when we go from gas to liquid, we call that condensation, right? So think about when you take a shower, right, and there's steam everywhere, right? After you've cut your shower off and the room's kind of cooled down, the mirror's covered with water, right? And you go to wipe the mirror off, it's all fogged up, you wipe it off and your hand's soaking wet, right? Where did that water come from? You didn't spray water on the mirror, right? Obviously. It came from the steam or the water vapor in the air. Right? So when that hot steam interacts with the cold surface of the mirror, it removes the heat energy from that steam, and what you're left with is liquid water, right? Same reason that there is, dew on plants. When you wake up in the morning, it didn't rain. It's not wet because it rained. It's wet because water vapor in the air cooled down, hit those plants or the ground or whatever it is, right? And you're left with water. And then lastly, from liquid down to solid, we call freezing, right? So when you freeze something, it's literally the act of turning something from a liquid into a solid, right? And that again is just removing heat. You're taking away heat energy from water, in this case, in our example, and turning it into ice. So real quickly, before we do some practice questions, there are also two other terms down here that we haven't mentioned. Oh, and where is, this is an old PowerPoint, so bear with me. I think it must be, I might not have. But I do want to talk about the instance when you can actually go from, so down here, sublimation is when you have a solid that turns directly to a gas. So it's possible under certain circumstances and with certain materials that you can take a solid and turn it into a gas without having it pass through a liquid phase, right? And a couple examples, and these aren't perfect examples, but they paint the picture. So if I had Alex here, he would critique me and give me a more scientifically accurate example, but I do not. So I'm going to just give Mike's example. And so when we talk about sublimation, frost is a form of sublimation where you have water vapor in the air and temperature drops really rapidly, really quickly, and you get that water vapor hitting plants or hitting the ground or hitting your car, and that extreme cold turns that water vapor directly into ice cream, right? It isn't like it hits your car and turns to water and then freezes. It does it all in one step, right? Another, oh man, what am I doing? That's the opposite way, damn it. Mike, you screwed it up. That I was just describing was going from a gas directly to a solid, which let's see. Caleb, I'm unmuting you. Do you know this term off the top of your head? It's eluding me right now.
We're going from a gas to a solid?
Yes.
Oh boy.
God, I know it too. Sorry, I'm putting you on the spot.
Okay. Gas to a solid. The clicking sound is my brain working.
Yeah, exactly. I know.
Deposition.
Deposition. Yep. Thank you, sir. Man, what a good wingman. Deposition. Yeah, that's what I was looking for. So that was the process I was just describing, right? So when you have a gas, it goes directly into a solid without becoming a liquid. That's deposition. Whereas sublimation is the opposite, where you take a solid and you turn it directly into a gas. So one example I give with this, and it's not a perfect example because there's more chemical reactions at work, but take burning fire, right? You take a log and you heat it up under extreme circumstances, right? Like set fire to it. That solid piece of wood becomes smoke, essentially. Now, there's other particles that end up, and again, there is other chemical reactions that go into why that transition happens. And again, Alex would, I'm sure, correct me. But just to kind of give you an example, right? When you heat up wood, that wood doesn't melt, turn into liquid wood, and then turn into smoke. It just goes right from wood, right? So anyway, long story short, there's some terms for you to kind of know, but I don't want to go too much beyond that. This is another kind of way of looking at the same thing we've been talking about. So this just shows you that matter transitions into different states as you increase energy, right? So as we go from left to right, from solid to liquid to gas to plasma, energy is increasing, right? And the reason that there's kind of these steps and that it's not like this, because if you take a solid, that solid doesn't gradually turn to liquid. That solid stays solid until it reaches what we call the melting point, right? So, and at that point, it then instantly becomes water. It isn't like there's this gradual transition where it gets a little bit gooey or something and then is like half solid and then turns to liquid, right? A solid stays a solid until it reaches a point at which it no longer becomes solid and then it instantly becomes liquid. That change happens at each one of these steps, right? So when liquids become gas, right? When liquids become gas, that's the boiling point, right? And it goes instantly from liquid to gas. So just a quick tidbit to think about, and this goes for everyone watching this video not live, right? We're pre-recorded if you're watching this on Facebook or YouTube. One or two things that almost every student that I ask this question to doesn't know. And I want to make sure everyone knows the freezing point of water is water freezes at 0 degrees Celsius or 32 degrees Fahrenheit. So if you knew it, good, and if not, make sure you remember it, right? And then the one almost no one knows, boiling point. The boiling point of water, other than we know maybe it's 100 degrees Celsius, that translates to 212 degrees Fahrenheit. That's kind of a side note, but I mention it because I talk to so many students that don't know it, and it's just some random facts that you probably should have in your brain. So there you go with that. So let me stop this screen share, and I'm going to pull up some questions. And yeah, going okay on time. So let's share a different screen. Okay. All right, so let me share this. All right, so I'll zoom in, and we're just going to do a couple of these because there's a few of these that are pretty dumb, and I don't really like them. But let's just start with number one. So, which of the following physical changes involve adding heat to a substance? So, pretty straightforward, right? Man, in the nick of time, you must have heard me talking about him. Alex is on now. Oof. Thanks. Alex, you came in just in time to not critique my science.
Did I really?
Yes.
Oh, lucky me.
Yeah, well, lucky me.
You should have seen my class earlier today. I did a whole thing on earthquakes in Washington. How
Really?
was it, Allie? Was it as great as I'm describing?
Sure.
See? That's how amazing it was, Mike.
Wow, that's pretty good.
Solid
All right.
recommendation from Allie.
Okay, Allie says it's good, then it must be. All right, well, Allie, let's finish up this rousing science class. You got 3 instructors and you all together in one spot. So, question 1, which of the following physical changes involve adding heat to a substance? A, melting and boiling. B, boiling and condensing. C, condensing and freezing. Or D, evaporating and condensing. Only 2 of those things are adding heat energy in this direction. And the answer is A, melting and boiling, right? Melting is going from solid to liquid. Boiling is going from liquid to gas. All right, so let's do at least number 2 here. So let me zoom back out. So number 2, density is the amount of mass in a particular volume of a substance. It can be expressed in grams per cubic centimeter. So in other words, how heavy something is per how big it is, right? That's what we're talking about with this. And heaviness is relative to gravity, and so I don't want to get into Alex critiquing me anymore, but you get the idea, right? So which of the following statements is supported by the information provided? So we have this chart of densities where we've got solids, liquids, and gases, right? So under solids, we have lead, which is 11.35 grams per cubic centimeter, iron 7.87, aluminum 2.7. Right? Under liquids, we have chloroform, which is 1.49 grams per cubic centimeter. Water is exactly 1.00 grams per cubic centimeter. And ethyl alcohol is 0.79. And then under gases, obviously you can see that they're much, much less dense, right? Like almost nothing. So think about that. Like anything over a density of 1.0 is going to sink in water, and anything under a density of 1.0 is going to float or be suspended in water. Right? So based on, and again, not based on things you might know or things you might think, just based on the chart. So just based on this chart, which of the following statements is supported by the information provided? A, water is the least dense liquid on Earth. B, solids are usually denser than liquids and gases. C, density increases as the volume of a substance increases. Or D, density decreases as the force of gravity. So again, we're just looking for what statement we can say is probably true based on the information that they have given us, right? So let's just kind of run through them real quick. A, water is the least dense liquid on Earth. Well, we know it's not because we can look on this chart and we know ethyl alcohol is less dense than water, right? So that's not true. A, throw it out. B, solids are usually denser than liquids and gases, okay? Up here, solids have a higher density. The liquids that they've given us have a lower density, and gases have even a lower density. So B looks to me like it's the right answer. Let's make sure that we're not missing something. So C, density increases as the volume of a substance increases. Okay? Remember, volume is just the amount of something we have. So there isn't anything on here about volume, but think about that. If I have water, a cup of water, and a giant bowl of water, or a swimming pool, the water is still going to be just as dense. It doesn't get more dense because I have more, right? So C is false. And D, density decreases as the force of gravity decreases. Without getting into an explanation of whether or not that's true or not, right? Just based on looking at this graph, there isn't anything even mentioned about gravity or its effect on density, right? So even though density decreases as the force of gravity decreases, may be a true statement. I'm gonna mute. Right, Alex? What do you got?
Sorry,
I'm gonna put you to work.
I was only halfway listening. Let's
Yeah,
see.
man.
Density
Well,
increases.
if I see your name on here, I'm gonna harass you a little bit.
All right, please do. Please do. So
Density decreases as the force of gravity decreases. That's a true statement, right?
No, actually, density is a constant thing. So
because density goes off of mass and not necessarily weight, it's not affected.
Weight itself would decrease as the gravity decreases. So
right,
that
but
part,
not the actual density.
But as you were saying, Mike, that really has nothing to do with that chart up there.
Exactly. Right. So that's I always am mindful of not making false claims, and even more so when I know that you are listening.
Do you want me to leave? Mike,
I'm giving you too hard. No,
dude,
I actually enjoy having you in class. You can attend any science class you want. I'm just giving you a hard time.
I can give you multiple reasons why you are a better science teacher than I am. And I'll give you the number one real quick right now. It's because I tend to overcomplicate this stuff. You bring it down to a base level, which is what they need.
Well, base level is where I operate, Alex.
Oh, I didn't mean that came out off as an insult. I am sorry.
No, I think we all have cabin fever. So we better get back to the end of this question before I get too derailed. But thank you, Alex.
What I'm good for.
Appreciate that, and I always appreciate your help. You should come to any science class you want. All right, but long story short, Allie, is that whether or not it's true or not, it doesn't matter in this context of the question, which is the bigger point I was trying to make, which is don't get hung up on what things sound good or sound right or might be right in something like this where you are looking to see what is proven to be true based on just what they've given you, then don't assume anything other than what you see in front of you. Okay, so in this instance, B, solids are usually denser than liquids or gases that's our answer right there. Okay. So let's stop there. And if you or if anyone else for that matter want more materials, just ask us and we can get you stuff to work on. So if you want more of these questions or you want different types of questions, just contact us through the website or email us. We'll get you spread away. Or like you have the resources that Youth Build, so Youth Builders can get resources that way. So with that, I'm going to go ahead and stop it for today. That's the last class for today, but we'll be back tomorrow, as far as I know, with the same schedule, same exciting classes. Okay? All right. I'm out of here. I'll talk to you all later. And Alex, thanks for letting me harass you a little bit.